Hi friends, welcome you all to the 18th session of home-based development. So in today's discussion we will be touching upon instructions. Now actually in the last session I have covered how thumb is implemented and what is the background of thumb design and the philosophy of the thumb design, and then why does anyone require that mode. Okay, so we have a good understanding of that now. So we will look at the thumb instruction in this session. My intent is not to go into the details of every instruction as we did for ARM instruction set, okay, because there is not much of difference except that it is these instructions are subset of this. So I will give you a summary of all the thumb instruction, and I would expect as a assignment, you can look at every instruction of thumb, and then maybe you can write a difference between what is ARM, okay, and then what is supported in ARM, and then what is the difference in the thumb mode, okay, the instructions, thumb mode instructions. So I would like to give it as an assignment of looking at all the instructions of instructions supported in thumb state, okay. So in this discussion we will be just giving you, I will give you some major differences between ARM instruction set and the thumb instruction set, and then we will carry on with the interrupt processing module, okay. So the topics that are going to be covered, I will touch upon this push and pop instruction which you have not seen in the ARM state, and then some minute differences in the conditional branches implementation in thumb state, and then I will give you a summary of all the instructions with a major high level difference between what is there in ARM state and how does it differ in the thumb state, okay. Then we will spend a majority of the time on interrupt processing in this session. Followed by this, in the next section we will go into the actual implementation of some of the interrupt handlers, okay. I will show you some assembly implementation of the couple of implementation of interrupt processing, and then we will go into the details of how it is done, okay. So that's going to be the next section. So in this section this is what is going to be covered. Okay, push and pop, if you are familiar with x86 processor, okay, you might have seen this instruction, okay, already. So thumb state has a similar push and pop which you didn't see in ARM state, okay. So I will show you what is the difference, how push and pop differs from the instructions that we are used in ARM state. Okay, so now you can see that the instruction length is only 16 bit, okay. This is the encoding of the thumb instruction, okay. Totally 16 bits are there, okay. This particular bit pattern, okay, all of them refer to this push or pop operation, okay. And then we have one bit reserved for whether it is a load or store. Please remember, push and pop is actually a stack operation, okay. Let us draw a stack, okay. This is a stack, and this is a lower address and this is a higher address. Now assume the stack is stack pointer which happens to be R13, okay. Remember, in thumb state R13 is only assumed to be a base register for the stack operations, okay. This is a stack, okay. This particular register only could be used with the push and pop. It always assumes when push and pop instructions are used, the R13 is picked up, okay. Whatever is the address stored in R13 is what is assumed to be the stack pointer, okay. So whenever you are using push and pop, make sure that R13 is initialized with the proper value and then use them. And one more assumption is, if you remember, there are so many modes, right, full and decrement, right, and then we have full and increment, and empty decrement, empty increment, right. That means when the stack pointer is pointing at whichever location, it is assumed to be full. That means it is already filled with some value. So when you want to do a push operation, okay, it is already pointing at full, and then what are we supposed to do? Decrement the pointer. So R13 is supposed to decrement and then load the first value in push. Suppose this is the current location where the R13 is pointing at, and then we have an instruction push, okay, and format I will tell you, but suppose you have put R2, okay. Please remember this can be only from R0 to R7, okay. Only these registers could be used, but there are special cases where R14 and R15 will be used, but for a generic purpose only these registers are can be used with a push and pop. Now when we do push R2, suppose what are we trying to say? R2, whatever is the content of R2, which happens to be some 32-bit value, needs to be pushed into the stack. But in the instruction we are not mentioning whether it is a decrement or full or empty. We are not saying about that. So it is implicit in the thumb state. It is always assumed that the stack is going downwards. That means from the higher address to lower address. Okay, from higher address to lower address, it is growing. Why do we say growing? When we push something into the stack is growing because more items get into the stack. So when we push, it is growing, and when we pop, it is decrementing, right? It is decreasing. The number of items in the stack is coming down. So effectively, when we do a push, we have to assume whether it is pointing at the empty location or a full location. But here in thumb state, it is always assumed that it is pointing at a full location. That means already some value is there, so it won't write into that location. It will decrement it by how many bytes? 4 bytes, because we are pushing 32-bit values into the stack. Please remember, in the thumb state also the data is assumed to be a 32-bit value. Okay, push and pop always does a 32-bit push and 32-bit of by pop operation. So a 32-bit value, that is 4 bytes, are pushed into the stack. So R2 will come here. The value in R2 will come here, and stack pointer will point at this location. That means what will happen? It will automatically get incremented to the address where it is currently pointing to. It is not incremented here because it is going down. So it is decremented by 4, and then it is pointing at R2. So this is how stack grows in the thumb state. Okay. So how is it converted? Whether you are giving a push or pop, based on that, this will be, see, this is the CPU and this is stack. So we are writing into this for push into the stack, and then we are reading it from stack for pop operation, correct? So it will correspond to what? It will correspond to store in the ARM, okay, and this will correspond to load, LDR. Okay, we are loading some value from the stack into the register. This is the CPU. Okay, so push will correspond to store. Okay, if you say pop, then it will be, this bit will be set. Pop, this particular bit will be set when it is encoding this instruction. Okay, and then these are all stand, always 1 and 0, and R. This is another 2 registers. See, if you recall, I mentioned that in thumb state only R0 to R7 could be used in all the instructions, and then some of the high-end registers could be used, okay, selectively. So, and then also I said that the job of each of these higher registers are fixed. That means R15 is always assumed, okay, it is true with ARM state also, is PC, and R14 is for link register, okay, and R13 is stack pointer. So this is not actually fixed in the ARM state, but it is fixed in the thumb state. R13 is always assumed to be a stack pointer. That's what I mentioned, that push and pop will always assume that R13 is what is used as a pointer to write into the stack, and then it is automatically decremented or incremented based on push operation or pop operation. So that write back also is assumed. Okay, we are not we don't have a choice in making whether this write back happens or not, because in the stack operation you want the stack pointer to point to the next location, otherwise we will be overwriting on the same thing that we have pushed earlier. So it should get decremented as we push, and then it should get incremented as we pop. Okay, that is what happens. So register list, let us go back here. Register list has 0 to 7. That means if you are pushing a value from R0, this bit will be set. If you are also pushing R1, this will be set. Suppose only R6 is pushed, this bit will be set. So we can give an option of which are the registers from R7 to R7 could be pushed into the stack or popped from the stack. Now what happens to these other registers? Especially this R14 is very important, because when we are doing a branch with exchange, the subroutine call, it moves to some other location and then comes back to the next instruction which is below the branch linkage, right? Or when you want to do a exception handler, it goes to the exception handler and then it comes back from the exception handler. So the return address where it is supposed to come back is always kept in R14. So there is a requirement that this R14 value is also need to be saved into the stack to avoid overwriting of this R14 by some other branch instruction or some other exception. So moving R14 into stack is a must. Okay, some occasions. So that option should be there. Just because it is in thumb state and we say that only R0 to R7 could be saved into the stack, then we have a problem in supporting the exception handling in the thumb state. That means in the thumb state exception should be recognized and then it will go to ARM state and then exception will be handled. But we should be able to respond to exception and come back from exception. That means the link register is a very critical piece of value which needs to be preserved. If we want the return value to be untouched. So R14, we should have some means of pushing the R14 value into the stack. That is why there is a selective bit provided for that. Okay. So okay, now you may wonder how do I use it. So I will show you an example. So push, if you have, and then you have a register list, then you can say R0 or 1 or whatever, R4, comma. When you are pushing, you can say that I want to push the value of R14 also into the stack. And then when we are popping it, we have to say this R14 has to come back to PC. So same register set you write R0 to R4, R0 to R4, no, it is R0 comma R4. So I will say that, and then I will say PC. That means what? The value which was stored in the stack, which happens to be the R14 content, now comes to a PC. That means that is the return address where the processor should come back to. So when we are pushing, we can mention that as a PC, and when we are when you are popping out value, we can mention it as a PC, and when we are pushing it, we can mention a R14. So these two, though they happen to be the higher part of the register set, okay, we said low and high, okay, but we could use R14 while pushing and then R15 while popping the value. So only these two registers are allowed. Okay, you can't write the reverse, because during the load and store, these bits will be, once you mention these registers, it will set this bit, okay, over encoding, and the processor automatically assumes if it is a push operation, it will, because it will know that whether push or pop based on the load and store. And then it will know whether one more register is mentioned, it will assume it will be R14 while pushing, and then it will assume that it is a PC while popping the value. Okay, I hope this you understood. This is very important piece of information. Okay, so optional storing of R14 link register along with low registers mentioned in the list on push, and then restoring the value which was loaded from R14, okay, into R15. Okay, that is, you cannot write while restoring back, that is while pop operation, we can't write R14. We have to say it is, you want to pop into PC only. Okay, maybe assembler will give an error if you do that. Okay, fine. Now I am giving you the details how to use it. Okay, this is the syntax of the push and pop operation. So we have to have just a flower bracket with the values. Okay, this is the syntax. Now you see the bit which are chosen. When we have LR, this bit is set. Okay, and then when we have PC, this bit is set. Push or pop, whether load or store, is chosen based on this. Okay, and then automatically inside that, who does this conversion? If you recall, the decompressor. Okay, decompressor inside the decode logic of the processor. Okay, this is a decode logic, decode stage of the processor. This is fetch and then execute. So during this decode stage, this instruction what we gave as a thumb state instruction like this push gets converted into this internally, and then from here onwards this is a typical ARM instruction, and then with this syntax. So now you see R13 is assumed everywhere, and then write back is also assumed everywhere, because stack operation we will not do without a write back, right? So and then R list is just copied from here to this. Now what happens? This R list will have a mention of value from R7 to R0, which gets expanded here. Okay, though this instruction allows from R615 to R0 in ARM mode, ARM state, only these values will be restored, and then rest of it will be 0. Okay, that is the way sorry, the conversion happens. Okay, so push will be changed to and then STMDB. So decrement before. Okay, decrement before and increment after. So this is the full decrement. You saw that is a stack operation. Okay, LD we could do that, but when we are using the LDM, okay, this is the format could be used. Okay, if you recall the ARM state, we had a instruction to stack operation, and then the load store operations will have these different combinations, right? So always in the push operation, it thinks that it is decrement before. That means what? It is a full. It is pointing at the full content, and then decrement it before you store the value. So that means what? It is not going to overwrite on the location where currently the stack pointer is pointing at. It will decrement it before pushing the value into it. That is, or storing the value into the stack. Similarly, when it is popping out, it will increment after. That means it will take out this value and then increment it. Okay, so these two I have explained in detail in the in the session where we talk about stack operation. So while storing decrement before, while loading the value, it is a increment after, and this is understandable. And you see here only R15 could be there or R14 is there. See, we are not here, we are mentioning that, and that is getting implicitly transferred here. So it is communicating that information by setting this bit, okay, to the processor. So you have to have only these values in here. So I have explained to you the reason why this is required. Okay, when you want to save the return address and then restore it in the stack, we need this. So ARM state has allowed only mentioning the additional high register. Only these registers can be used in this instruction. So this instruction, okay, now I am not going to go into the details of instruction cycle times for the thumb state, because it is identical to that of equivalent ARM instruction. So if suppose you want to know what is the number of sequential cycle, number of non-sequential cycle or internal cycles, okay, if you know the value of this, okay, whatever is the cycle, the same thing is going to be for this. Can you reason it out? Think over. Why is it same as the equivalent ARM instruction? If you recall the instruction cycle times, okay, instruction cycle time is calculated based on how much of time that instruction spends in the execute stage. If you remember that, that was the definition of instruction cycle time. Now I just now explained to you, after the decompressor, the ARM instruction is what is generated from the decode stage, equivalent from thumb state to ARM state, and then that is what is getting executed. So do you see any difference between a push or a pop, between the time taken for push and pop with the equivalent ARM instruction? You won't see the difference, because this only is converted into ARM state and gets executed here, and our calculation of instruction cycle time is based on the time it spends in the execution stage. So it is as good as executing this ARM instruction, equivalent ARM instruction. That is why this can be reasoned it out. Okay, you can reason it out why it is same as this, because once this is converted, ARM in the execution stage, it doesn't even know whether it is executing this or not, though it can make out from the CPSR value. But what I am saying is, from the hardware perspective, it is same as executing this instruction. So it will take the same execution time as the equivalent ARM instruction. So good. Now let us see an example. Now suppose if we have this, what does it do? R0 to R4. So all the 5 registers are saved along with LR, and this is what is assumed. Okay, and then similarly this is what is assumed internally, and then it is restoring the values. See, the above instruction can be used to store the working register. Okay, suppose you want to use these registers in your subroutine or something, then you can save them and then start using them, and then return address you can restore it from R14. Okay, so it was saved by the BL instruction, and you want to call one more subroutine, then we should save the previous return address, otherwise it will be lost. So that needs to be saved in the stack and then restored before it comes back to the recursive. Suppose you want to call a function. From this function one more function is called, and from this function is calling one more function. A function call is same as a jump branch with the link register to some label, which is the sorting of the function. So this is F1. Okay, let me explain this once. Okay, recall. Suppose this is what you want to do in your code, and then after this you want to come back here, and then you want to come back here. How do you do it? So suppose functions are returned. This is a code. F1 is starting here. Okay, and F2 is starting here from this location to this location. Okay, and F3 a function, another function which is starting from this to this location. Now currently the code is somewhere here. Okay, now you say BL, okay, to F2. Sorry, so suppose we are calling it as F1 is calling this F2, right? So let us assume that the code is here. Okay, and then it is calling branch to F2. Okay, BL for F2. What happens? This, from this particular place, it goes to this function call. Now R14 here would have had the value which is next to this address. Assume it is something, okay, some address, 108 something. Okay, so that value is written into 108. Okay, R14 is having right now. Now in this function you are calling one more BL. Okay, BL to F3. What happens? From this location it will jump to F3. Now what happens? This also saves in R14 the value, because it is in we are always assuming this is a lower address and this is a higher address. Okay, assume that this is some 206. Okay, please remember it is in thumb state, so I can write as 6 here. It's the 2-byte boundaries. Okay, core also can be 16 bits. Okay, whereas in ARM state I can't write 206, right? It is not a 4-byte boundary address. So assume R14 is 206. What does it mean? After calling this F3, it is supposed to come back to this address, which is 206. Now what happens? This R14, if it was not saved in the stack, it is overwritten now with this address. So when you return from here, you say that you save R14 value into PC, then what happens? It comes, the control comes here, but you cannot now bring the control back to F1 because we don't have the previous address which was written into R14. BL automatically saves that value in R14, but it doesn't know whether one more BL is called or not. So this R14 will be lost if we don't preserve it in the stack. That is why I am saying the reason for preserving the R14 value in the stack is to, if you want to have a function calling another function and we want to return back to the original caller. So what happens if suppose you have saved this R14 into the stack, then this wouldn't have overwritten that value. So you can, after you come back from here, we can save it, restore that value from the stack here, and then call another, copy that R14 to PC, okay, move back to the original caller. So this kind of a function calling is possible only when we save the R14 in the stack. That is the reason the ARM state also has to support this particular saving of this into stack. Okay. Otherwise, come state we will not be able to call functions inside a function or exceptions inside an exception. Good. So I hope this is clear to you. If you don't, this is very critical point of thing understanding. So please pay attention to this. So this is how BL is used to save the value in R14 and then restore it from PC. So POP can be executed from the return from a function call to calling. Okay. So note that while loading the R14 value, it is moved into R15 to transfer control back to the calling. So while loading the value of R14 is there in the stack, and the same thing which was copied from R14 is restored into R15. Okay, I have explained this in the previous lectures also, but I thought I will stress on this point again, because you may wonder why is it there in ARM state, because they want to support the calling of functions from inside another function. Now I will show you some conditional branch instruction. Okay, in thumb state. Again, remember this is the 16-bit value, and the offset value is restricted to only 8-bit because of the number of bits that you have is reduced now. Now there is a conditional flag. If you recall, in the ARM state, okay, the conditional flags were always at the high end of the instruction. It is user 31 and this 0. So these high 4 bits, right? They were having the CZNV. Okay, it's not CZNV, it is that value, that EQ or NE, those are the conditional things. Based on this, the CPSR CZNV was looked at, and then a particular instruction will be either executed or dropped based on this. What is the condition you have mentioned? If you recall, add EQ, okay, could have had some value here, and then this instruction will be executed only when 0 flag is set. Okay, it will check this 0 flag in CPSR and then decide whether to execute or not. If you recall, ARM state it supports, but thumb state does not support this conditional execution for all instructions. Okay, only except for conditional branch instruction, this conditional execution is not supported in thumb state. Why? Because there is no place for storing this conditional EQ or whatever 16 conditions are not possible to be stored in the 16-bit of encoding we have. But conditional branch is required, so they have introduced that particular conditional execution of branch instruction here. So these are the 4 bits which are used for that purpose, and then based on the conditional statement here, whether EQ or whatever is mentioned in the instruction, the corresponding flags will be verified, and then based on that the instruction will be executed. That means the branching will happen or it won't happen. Now one more important difference you should remember. If you recall, in ARM state, okay, whatever is the PC value when the current instruction is executing will be PC plus 8, isn't it? If you recall, that is what we were being told so far, because the 3 stages of the pipeline, the instruction will be 4 bytes down the line, it will be accessing it, right? That's why 4 plus 4, that's why 8 bytes ahead of the current instruction which is getting executed. Whereas in thumb state, the scenario is different, because it is going 2 bytes at a time. Okay, because it's all 16-bit wide instruction. Here 32 bits wide instruction. So if suppose this is 100, the next instruction will be 102, and the other one will be 104. So the PC value will be this is +2 and another +2, so 4 bytes ahead of the current instruction. So this offset value is computed assuming the PC is 4 bytes ahead. Okay, and what is the offset value stored here? It is a 2 byte address, 2 byte aligned address. So we can leave off the lower LSB bit of the offset because it is always anyway 2 byte boundary. So effectively this could be shifted to left by 1 bit, and then this 0 can be added here because this is anyway always 0 in a thumb state. Earlier, if you recall, in ARM state, it was shifting it by 2 bits because lower 2 bits of the address were always 0 in the ARM state. So that is the difference. So it will be shifted by 1 bit. Okay, so effectively we are getting a 9-bit offset. Okay, and then it has to be sign extended because this is a signed offset because we need to provide a support for either higher, suppose if I am showing the higher address is towards this side, plus we have to show for going into the higher address, and minus we have to give offset to go into the lower address if suppose I am writing the address in the this order. Okay, so that is the reason 4 bytes. So these are the typical examples of how do you write a branch instruction in the thumb assembler. Okay, and then these are the equivalent conditional flags which go into this 4-bit location, and then equivalent ARM will be this. So you won't see the difference between these two because internally it will be expanded into a 16-bit 32-bit instruction, that's all, and the function is the same, and the offset will be expanded because originally in ARM state it is a 12-bit offset, whereas here it is a 8-bit offset. So it will be sign extended to 12-bit and then stored in the ARM instruction. Okay, and stored as ARM before going to execute state. So let us see an example. This, please remember, this is a code 16 is assumed. Why? These are all thumb instructions. Okay, thumb state instruction. It's already in the thumb state. So we are saying that some compare with some value constant 45, and then if it is greater, R0 is greater than 45, go to this place. So this will be a thumb state, so it will move there. Okay, it is half word aligned because 2-byte boundary. Okay, that's all. While the label specifies a 9-bit 2's complement address, this will always be half word aligned. So originally it's a 9-bit offset which is written into a instruction as a 8-bit offset because it can always left shift it by 1 bit because the lower bit is always a 0. So here bit 0 is always set to 0, so it will do a arithmetic shift right. Okay, 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 while performing, okay, 8-bit value, okay, sorry, 9-bit value, offset value to be stored inside the instruction as 8-bit. Okay, so originally you will know that it will be 0 and some offset is there. If it is negative it will be 1, and then some value bits are there, 9 bits are there. It needs to be stored as a 8-bit offset in the instruction. So it has to do a ASR because this sign bit has to be preserved. Okay, it's a signed arithmetic, so it will be shifted into 8-bit. The lower 0 will go off, and then the remaining 8-bit will be stored in the instruction. That's what I am showing it here. Okay, and these two combinations are not valid here. Okay, that's how they have defined it. Okay, you cannot have a always when you have either you don't mention anything or you say greater than or some other combination. Very good. So let me quickly cover the thumb instruction set summary. Okay, add with carry have a lower registers, only it will use, there is no high registers. Only some instructions of add will allow high registers to be mentioned. But please remember, whenever it is allowing a high register, not typically it will be R14 and R15, which are assumed based on the particular context of the instruction. Okay, so rest of the other registers are not normally allowed. Okay, because you know that internally the instructions are decoded as a 3-bit, registers are decoded as a 3-bit value. So there is no possibility of storing a 4-bit value for the register. So some instructions assume a standard R14 or R15. Typical example will be a push and pop. Okay, So I want you to go through all the instructions in the thumb state and then see the differences of all of them between arm and thumb. Okay, that's an exercise as an assignment. Okay, so I'm not going to go into the details of this. This I'm only just giving you which are the instructions support the typical high. If you see, it is allowed here in move because we want the R14 to be or R15 to be used in the instructions. Okay, when we want a return from effectively we want to use the stack value of R14 or R15 to be used. So move or even the previous branch or compare may use this higher registers as one of the operands. Okay, and then these all the instructions. One more minor difference is I mentioned it. All this ROR and then ORR, these are all barrel shifter operation which happen to be part of the instruction earlier in the ARM state, whereas they are all separate instructions in the thumb state. That's another difference you should be aware of. Okay, so that's it. We have done with the thumb state instructions. Okay, now we are moving into exceptions and associated modes. Though I have touched upon this earlier, I am using this particular session to just brush up what we learned in the earlier discussion, so that you will be ready for understanding the implementation of exception handlers. Okay, so I want you to pay attention to this, and if you have any doubts or clarification you need, refer the ARM document or refer to this lecture again, so that you are familiarized with this particular modes and how exceptions are handled, because I have mentioned it in so many occasions, so that you get this idea. Because when we see actual implementation, this background, this knowledge is a must. Okay, these are all the different exceptions. Okay, all of you are by now aware of all this. Okay, but I am just showing you they are all mapping onto which modes. Okay, these are the different modes which have different bank registers. Please remember, they all have some different bank registers. Different set of registers are banked. Okay, now see that couple of things map onto a single one. Okay, abort mode, data abort and prefetch abort both map onto single abort mode. That means what? A single abort mode registers, okay, bank registers, okay, are used by both the data abort as well as prefetch abort. That means when you are in data abort, if you are or if when you are in prefetch abort, if you are servicing a data abort, because prefetch abort is a lower priority compared to data abort, high priority. Okay, so if you are here and then you are servicing this, then what happens is the same bank registers are used. So we have to have some means of saving those values into the respective, within the stack pointers, okay, within the stack, so that when one abort is handling the other abort, we don't lose these values which were previously saved. Let me explain this once. Okay, again the example is R14, which is very important. Okay, now you see, I'll explain you. This is the user code. Okay, let us assume we are executing the ARM is executing in the user mode. Suddenly one prefetch abort has happened. Okay, prefetch abort has happened. Okay, now it will come to the abort mode and it will start using this R14 register, and in this R14 the return address, okay, where after this is, okay, this abort handler has been serviced, it should come back and execute the same instruction, because this instruction was not completed because of the prefetch abort. So it came here to the abort mode, and then the automatically processor would have saved the return address, that is this address, in this place of R14 of the abort mode bank register. Okay, now and then remember that SPSR also of this mode has also been saved with the CPSR value. Here CPSR was there, okay, in the user mode, which got saved into the SPSR of abort mode. Now assume when we are in this handling this prefetch abort, okay, this is a prefetch abort, a data abort happens. Okay, So what happens? It will go to data abort handler. Okay. So now data abort handler also uses the same abort mode, because you see that prefetch abort also mapped onto the same mode, abort mode. That means they will also use the same mode register, same SPSR, same R14, same R13. These are the registers which are banked. So now what happens when this abort is recognized and then it goes to the abort handler, it has to say currently what it is being doing. So it is executing the prefetch abort handler, and then what will happen? This will be overwritten with the new return address. That means suppose prefetch abort was here, and then during that handling of this instruction, the data abort has happened because it was trying to access something in memory, and then which has resulted in the abort. So it comes here. Now this address has to be executed. It has to be saved. So now what will happen? This will be overwritten. This address which was earlier saved is overwritten by this address. Now we cannot come back at all. Our processor cannot come back here. So what is that need to be done? In the prefetch abort handler, we need to save this R14 and R13 into the stack pointer, into the stack. So stack is going downward, so it will be saved here, and then now new abort happens. This can be overwritten, no issues, because anyway we have saved these values in the stack. So after performing this data abort, we can always come back and then restore it from the stack and then come back here. Okay. So this is what is a sequence of aborts happening might override this register, so which needs to be saved. Okay. This I will be explaining in the handler class in the next maybe next session. But I just want to tell you, you should understand this particular thing in your mind. You can, if you don't follow this, please read up more, have a clarity on this. And similarly, supervisor mode has both SWI instruction as well as reset, brings it here. Okay. So anyway, after reset we don't have to come back at all, no problem. But SWI can have one SWI, okay, may call another SWI inside. You may write the code like that. In that case, what will happen? The same bank registers of the supervisor will be used, so we have to save it in the stack. And okay, that is why we need to have a stack for each mode. Okay, please remember. Okay, I will explain you a sample code here in this session, so that you understand that the need for a stack, because stack is going to keep the registers which are likely to be overwritten in the stack, so that you are not losing those values. And then the programmer, as a handler writer, we should remember to pop it out where whatever we have pushed into the stack. Please remember, stack is always not going to be overwritten. As long as it is, you have a sufficient space in the stack, we can always read back the value that we have pushed into the stack. That is why we want stack in each mode, so that a recursive function call or a handler calling another handler, abort one abort, during the one abort being handled, another abort handling coming up. All these things can be managed if we have values saved in stack. So each of the above modes have its own bank registers. All the above modes are privileged modes. Okay, they are all privileged mode. What I mean by privileged mode? In the privileged mode, you had a right access to the mode bits of CPSR. That means when we are in a system mode, we can write into mode bit to go into any other different modes. Okay, I will explain you with the code. So, but you cannot do that in a user mode. Once we are in user mode, we can't write into the mode bits of CPSR. Effectively, we will not be able to change over to any other mode. Okay. So only system mode we will be able to do it. That is why on reset the processor comes up in system mode. Okay, it is it's a supervisor mode. Both the supervisor mode. Okay, so supervisor mode also has a. I will explain about the system mode separately. Supervisor mode has it's a privileged mode, so you will be able to write into the mode bit. So when on reset, when we enter the supervisor mode, the OS will take a control. Okay, typically on reset, the initialization code of our embedded processor, or if you are using a OS, that OS will come into action first. So the OS will decide where the stack needs to be for each of the modes. Okay, and then they write into the R13 of each of the mode, because R13 is the stack pointer, right? Default. So those registers are used to point to different stacks, so that when we come to user mode, after that if IRQ happens, interrupt happens, or FAQ happens, or any other abort happens, we have the stack already initialized. Okay, so we can save the values into those stack if like I mentioned previously, so that we can get back those values later on. So user mode does not have write permission to the mode bits. Okay. Now I'm just recalling, the bank registers. Please remember the fast interrupt has some more bank registers. That means what? These registers are masked, okay, by this set of registers. So we can always, we don't have to bother about saving them in the fast interrupt request handler, because they are masked by its own registers. So we can use them without any problem. We don't have to worry that whether user mode registers have been overwritten or not. Similarly, in these cases, we have our own mode registers, sorry, the individual bank registers. So it will be used for individual modes in the individual mode for its own purpose, and then SPSR is to save the CPSR value here. Okay, so please keep this in mind always when we talk about abort. You have to remember that when the processor enters from user mode to this, or from maybe it is in prefetch abort it is handling, and then it is supposed to come back to fast interrupt. The time fast interrupt happens and it comes here, then this will be it won't be accessed. Now it will come, this registers will become active. So whichever mode the processor is in, those mode registers, bank registers become active automatically, and then the balance user mode registers become active. That means they are visible always. In this case, only this will be visible and this is shadowed in the fast interrupt, whereas in other cases up to this point the user mode registers are visible. That means your whatever value is here, you will be seeing it here also and here also. Unless you save them, you cannot use it in this handler, because you will be overwriting what the user has kept it there. You may not even know whether user has used these registers or not. So handlers need to always assume that these registers are used by somebody else. So whenever we are trying to use these registers in the handler, we need to save them. Okay, as a programmer writing the handler routines. Okay, so you have to have a clear idea of all this. Okay, the system mode is little bit different from other modes. So I thought I will explain you. See, if you see here, user and the system modes use the same set of registers. Okay, they have the view of the same set of registers. Then you may wonder what is the difference. That's what I'm going to tell you in the next section. Okay, all the modes except user mode can change the processor mode bit. Okay, by writing directly into the mode bits of CPSR, whereas user mode you cannot touch the mode bit. Now, if the system mode, what is the use of all processor modes except system mode have a set of associated bank registers. What I mean by that? See, let me go back. Except for the system mode, all other modes have a set of some bank registers, right? Whereas system mode does not have any bank register. It has the same user mode registers visible to it in the system mode. Now you may wonder what is the difference then between the user mode and system mode. The difference is system mode has the same set of user mode registers, but it can also change the mode bits in CPSR, whereas user mode cannot do that. So that is a major difference between a system mode and a user mode. Though they have the same set of registers visible to them, and system mode does not have any bank register, but it can change the mode bits. Okay, it has got some write permission to the CPSR. So that means what? In system mode, processor it can change the mode bit to get into any other different mode, IRQ mode or FAQ mode, any mode. So that is why OS is residing in system mode, whereas user code will be in the user mode. Okay, so that means what? User cannot change the mode, whereas as a OS code running in system mode can change the mode bit. Okay, that is a major difference. System mode cannot be entered by an exception. Another difference in system mode is it cannot be entered through an exception. What I mean by that? Suppose you know that prefetch abort happens, it will go into abort mode. If data abort happens, it will go to abort mode. If external IRQ interrupt happens, it will get into IRQ mode, correct? And if FAQ interrupt is happening from the external system, it will enter the FAQ mode. So we can enter through different SWI. Suppose you are executing SWI instruction, it will go to supervisor mode. So we have different means of entering into these modes, whereas system mode cannot be entered through any of these external things. Only way is by changing the CPSR value. Okay, so there is a separate mode bit, the 5-bit values 0 to 4, correct, 5 bits in the CPSR is reserved for the mode bit. By changing some value which is equivalent to some system mode, we can go into the system mode by not by any other mean. That's what I'm saying. Okay, so corruption of link register. So this I have already told you. In case if you want the registers to be preserved, the system handlers what they do is they move to system mode. Okay, that means abort handler is there. Okay, I explained you some way that if suppose you want during the data abort mode, prefetch abort mode, if we want a data abort to be handled, the one way of doing it is you save this register and then you come to system mode and work on it. Okay, what is the why we are thinking that system mode is safer to execute? Because through different external event we cannot get into system mode. Only by changing mode bits we can get into system mode. So this is little bit safer. Okay. But at the same time any other handler can also come into system mode by changing the mode bits, because all the privilege modes have the right to change the mode bits. So system mode is used for handling a higher value. If suppose you want to execute more amount of information, more amount of code, then the abort handlers normally come to system mode. Okay, I don't want to explain so much here, you may not understand it. Now we will go to the, when we come to the next session we will have a more detailed discussion on this. Okay, only remember that system mode is also used by other handlers to come into system mode to execute it, because we allow by changing the mode bit we can always allow any other mode to come to system mode and use the user mode registers freely. Okay, but we need to save them in the stack before using them. Okay, that is very important. Okay, of course, very good. So system mode can run tasks that require privilege access. So because I told you that system mode has the right permission to CPSR. Okay, good. Exception handlers. Typically an application runs in user mode, but handling exception requires privilege mode, and we have already talked about this in detail earlier also. Whenever exception change mode it enters, it will get its own stack pointer, its own link register, its own SPSR, and FAQ will get more bank registers. I explained you in detail by showing the bank registers. Okay, these are all we are talking about bank registers here. Okay, nothing new. Each exception handler must ensure that other registers are restored if used by handlers. I told you that also. If suppose you are using any other registers apart from what we have in bank registers, that needs to be saved. Otherwise, it will be overwriting on the previous value. It can be saved. It can be done by saving the contents of any registers into the stack on its own stack. Okay, and then restoring back while returning them. Now I will explain you what I mean by own stack. Before that, let us just see that how processor responds to exceptions. So it saves the CPSR into SPSR of the mode, and if it is in thumb state, it moves to ARM state, because exceptions can be handled only in ARM state, and then it changes the CPSR modes to the mode it is going. Suppose IRQ mode it is jumping because of interrupt, IRQ interrupt, it will change it to CPSR to IRQ mode, because it has already saved the previous value in the SPSR. It can happily change the value. And then I explained this also, that whenever it goes into some register, IRQ is always disabled. Whenever it enters any other abort mode, okay, IRQ interrupts are disabled always, whereas FAQ is not touched, unchanged, except for when it is getting into FAQ mode, it is disabled. Okay, so this is why is it done, because one interrupt calling, when it is handling one interrupt, this doesn't want to be interrupted by the same interrupt. So IRQ is disabled always, and FAQ is disabled only when it is servicing FAQ interrupt, because FAQ has a higher priority than IRQ. And then it also sets the appropriate link registers with a return value. Okay, and the PC to the vector address. This is anyway it is jumping to the exception handler by going to the particular PC address. Okay. So now that is the way it is responding to the ARM processor is responding to any exception. Now I told you that we need to have a stack for each of the mode. Okay, how can it be set up? I am giving an example. Okay, now these are the bank registers. These are the R13 registers of each bank. Okay, they need to be initialized with the different values. Okay, that means what? Different locations in the memory are used for each of the stack. Because we can't have all the stack pointing to the same location. Otherwise, every mode will be writing to the same location, and then we won't be able to save the values. So they need to be saved in different stack. So before any of the mode are enabled or IRQ or FAQ is enabled, these stack pointers need to be initialized. This is one of the job of the reset handler. Okay, on reset, these R13s of each mode should be initialized with the different values so that they have a different stack. Otherwise, the user handler should be aware of it. Okay, the stack or say they are all pointing to the same stack, which is very complex in implementation, as well as it is very difficult to debug also if your code is not running or your application is crashing. Okay, so each mode having different. Okay, friends. So we have different mode bank registers with a different registers R13 pointing to used by each mode. Okay, so these R13s are actually used for stack. So whenever you do something you want to write into the stack, then we will be using the R13 to push the value, right? So now we need to make sure the stack when we are pushing it is decremented and then value is pushed into that. That means the stack is growing. So in a different modes, suppose different handlers may be there, different IRQ or FAQ may happen, and each of them may be using the stack. It may be pushing some values into the stack. So they cannot be pointing into the same location in the memory. In that case, what will happen? All of them will be pushing into the same stack. Then restoring will be you have to be handled properly, and then we also make sure that if suppose there is a problem in the program, debugging would be very difficult because every mode is using the same stack. So to avoid that, each of the stack registers, okay, R13 can be initialized with the different addresses. Okay, allocating some space, sufficient space in the stack. So okay, suppose if you think particular IRQ mode, you need only 10K bytes of stack. Then you have to make sure that the handlers in the IRQ mode do not push so much into the stack beyond 10K. If it does so, then there is no direct hardware implementation of checking whether this is exceeding the stack. So what will happen if IRQ is exceeding? It will get into FAQ stack and then start corrupting this stack. So different stack supports easy to manage, so that we have a different memory allocated for each of the stack. At the same time, we have to also make sure that the stack doesn't overflow into the next location. Okay, so before enabling any of these interrupts or any of this mode, we should come and then make sure that this R13 of the registers are all initialized with the proper values. Okay, because on reset they are all having a different undefined values, so we don't know what it is having, so we have to initialize them. So that is the job of the reset handler. Okay, let us see. Each of the exception modes have their own stack and then initialized by the reset handler. Okay, I will show you an example code and then we'll end this session today. So these are the different ways the memory can be mapped. Okay, so with the use of linker, we will be able to reserve different spaces in the memory and then initialize the relevant registers. Okay, if it is a stack space, initialize the different registers of different modes so that we have those initialized values so that those memory locations can be used. Suppose if we say that this is the location we are reserving for IRQ stack and this is the location we are using for SVC stack, then the R13 of that particular mode should be initialized with this value first, because once this is the starting address, it will be anyway growing downwards. Okay, we have to make sure that it grows always downwards. So in that case, we can always use, as long as it is used within this limit, it's fine. That is how the memory has to be handled. Okay, to manage the different handlers, different modes of the processor. Now, how do we set up the stack? Okay, I am giving a sample code here. This dot eq, you may not be able to see the from distance. It is dot, okay, eq. That is a syntax used by the our ARM sim that we use for our lecture here. So what we are saying is it is equivalent to hash define in C. This much value. That means we are saying that this much of stack is required for IRQ. This much of space is required for the FAQ stack. Now these are the different mode bits which are defined by the ARM processor. Okay, these are the lower 5 bits need to be this if you want to enter into these modes. Then what is this mode mark? This is the lower 5 bit value. Okay, that is all 1F is stored, and then you remember dot dat is the starting of the dot data segment, because the stack is a read write segment, right? It needs to be read write. We cannot have a ROM map to the stack because ROM is only read only. So it has to be a data segment where stack is pushing into it. That means it is writing into it, and then when it is popping, it is reading from the stack. So stack location is a read write location. It is similar to a data location, right? That is why we have to choose a data segment with a read write permission, and then this dot skip gives a indication to the linker that this much of space needs to be reserved for it. So it cannot use this location, whatever is the starting address, wherever it is starting up this segment in the memory. Okay, it may decide to start from some location. Then from that place onwards, the 0x8 should be reserved for 8K, should be used for IRQ. So it cannot allocate the same location for maybe another FAQ stack or some other data segment or some variable. So it is an instruction to the linker to reserve the space for this particular usage. Okay, but this is not enough. If you say IRQ stack, processor doesn't know that it is used for IRQ. We have to initialize the R13 of the IRQ mode. Okay, that should be initialized with this value. Then only actually the processor will know that okay, I can use this particular space for my IRQ handling. Okay, so this needs to be done by whom? By the reset handler. That is what I am going to show you, the piece of code. Okay, assume that currently this mode is system mode. Why I am assuming this is in system mode? Only in system mode or some other privilege mode we have a option to access the CPSR mode registers. Okay, otherwise we will not be able to write into the mode register. You cannot be in a user mode and try to execute this code. It will not work. Okay, it needs to be in the system mode or a supervisor mode where you have a write permission to the CPSR. The mode bit values you can write into the CPSR. Now let me okay, do one thing. Let us not continue here. I want you to spend some 10 minutes. Okay, I hope that will be sufficient to understand this code before I start with the explanation, because I want you, because I explained you what it is, I explained you what are these. Now you should be able to understand what is happening in this code. I am telling you this is done prior to enabling any interrupt, and it is in system mode. Maybe you can assume it as a reset handler. Now this background is enough for you to know what is happening here, because you are all now experts in understanding the ARM instructions, hopefully, right? So please do that. I am sure you will be able to understand. Okay, take a 10 minutes break. Okay friends, I hope you had a good understanding of this particular code. Let us see. Okay, I'll explain it now. What is happening here? We are just copying the value, current CPSR value, into R0. Okay, and then this is what it will use, this value mode mask which happens to be a 1F, it will invert it. When it inverts this 1F, what will happen? The lower 5 bits will become 0, okay, lower 5 bits, and the remaining bits out of 32 will be all ones, okay, and that will be AND with, okay, big AND, okay, it will do a AND operation after this inversion with R0, whatever may be the value of R0 which was copied from CPSR, okay. Now what happens? Assume CPSR was having something, okay, some bits, conditional bits was there, and then some interrupt flags were there, and then lower 5 bits were there. So we want to preserve the lower bits, okay, we want to preserve whatever may be the previous value, we want to not to touch it. We are interested in only in this 5 bit value to be changed, okay, 5 bits. So by ANDing this CPSR value which is now moved into R0, what happens? This all this thing will be untouched, okay. When you AND it with, now this is the R0 value which has come from CPSR, now we want to AND it with all ones followed by 5 zeros. When you do this, this forcibly these bits will be in R0 will be made 0, and rest of the bit will be untouched. You agree? Okay. Please remember, we are just doing it with the R0 only, not with the actual CPSR which happens to be here. CPSR we are copied into R0 and then modifying the CPSR value, only modifying the lower 5 bits to 0. Okay, now that is what is done by this instruction. Now what are we trying to do here? IRQ mode. We are ORing it. Now the R0 previous content R0 is ORed with this bit. This bit anyway it is a low 5 bit value only, okay. So one of the modes, maybe we are picking up the IRQ mode 0x12, that we are ORing it with. Now what happens? We got in the R0, okay, R0 was up to 5 bit, okay, it is same as what was there in the CPSR originally. You agree? Okay. These are conditional flags are here, and then rest of it is anyway unused. But this lower 5 bits now becomes IRQ mode, okay. But still the processor is not in IRQ mode. Why? Because CPSR has not changed. So only R0 is changed. That doesn't mean that CPU, the processor will move to IRQ mode. So it is continuing to be in system mode up to this point. Please remember, up to this point the processor is in system mode. Let me erase. Now here we are writing into the CPSR. What value we are writing into the CPSR by changing only the lower 5 bit to IRQ mode. Now what happens? This processor now up to at this point after this instruction, it is in IRQ mode. What I mean by IRQ mode? Suddenly if you say the process is in IRQ mode, what does it matter? What does it actually? What you should keep in back of your mind? You have to remember in the back of the mind, the bank registers are visible now, which is meant for IRQ mode. Which are the registers? R14, okay, let me write it in the order. R13 and SPSR, they are all visible now, okay. This particular R13 is visible, not what was there in system mode, because I told you system mode uses the same user mode registers. It was having CPSR, right? Please remember, this register has become visible now, okay, but this is also there. But this R13 and R14 are not visible, which happens to be in the system mode or user mode register. This is masked by this register. So when we in this instruction we use R13, we are actually writing into this register, not the R13 which is here. Okay, R15 is here, so I have not shown this. R15 is here, which happens to be same. We are not writing into this register, we are writing into this IRQ bank register R13. That is what you should remember. And please remember, it is we are not going to write R13 underscore ABT or IRQ, all those things. Okay, it is assemblers may not accept that. You have to say R13 only, but we should remember in the back of the mind, this R13 now corresponds to the IRQ mode, because we change the IRQ mode here by writing into the CPSR. This instruction, you know what the C means? it writes only the lower 8 bits, okay, lower 8 bits of the value. Lower 8 bits of CPSR only is modified. This is not touched. So when it is writing in it actually we have changed this to IRQ mode 5 bits. So it has moved into IRQ mode. Okay, I hope this is clear to you. Now what happens? We are initializing it with the IRQ new stack. Whatever is the label which is starting here, okay, linker would have reserved some space. We don't know. Okay, once you see after the linking and all done based on your configuration you have given to IRQ, it would have reserved some space for this. So that address will be written into R13. So LDR is a load instruction, you know that, and then it is whatever the label correspond to which address it corresponds to, that will be written into R13 of the IRQ register, IRQ bank register. Now we are continuing here. Okay, IRQ mode itself we are continuing. We are copying the CPSR value into R0, and then mode mask we are doing. We are masking the mode, and then with the same big instruction which I don't want to explain again. Now FAQ mode is odd with this. So now we are changing to FAQ mode. Once this is written into into CPSRC, now the processor enters into FAQ mode. Now what happens? Earlier it was in system mode, okay, and then it came to IRQ mode. Now it is coming to FAQ mode. Now FAQ mode has two registers, right? 13, R13 and R14. Now these registers will become visible. Its own SPSR will be visible. This will not be visible. Even this R13 in the user mode will not be visible. Now when we write into R13, we are writing this particular physical register which happens to be for the FAQ mode. We are initializing it. So like this, from the system mode we can move to any other mode by changing the CPSR value, because CPSR is visible in all the modes. Okay, though SPSR is coming into each mode, okay, CPSR is also visible. Remember that. Only these are the bank registers which are masking this, but this is visible. So we can always write into CPSR and move to another mode and then write the new value. So this is how the stack of different mode are initialized. So please try out this particular instructions in your with the simulator, because you can use the simulator for this. Please try out and learn how it happens. So how can you verify it is using different registers? What you do this, you modify the R13 value here, right? You now change it to system mode. Okay, now you will see that R13 is having some different value, not this value what you are loaded. Then come back to the system FAQ mode, you will see this again. Go back, you will see this, or go back to IRQ mode, you will see this value. So you will be really understanding it by seeing in the simulator. Okay, then you will understand how the bank registers function. Please do this as a part of the lab exercise. Okay, so I am just explaining this. It is common for a user mode stack to be initialized at the end. Why? Okay, after doing all that initialization, user mode stack has to be initialized. It can be done only at the end, because once you come to user mode, okay, there is no way to go back to other modes. Okay, because user mode doesn't allow CPSR mode bits to be changed. So you are locked on. So you can only execute software interrupt or some other exception needs to happen for you to move to other mode. So from reset, before coming to reset user mode, all the stack pointers should be initialized. Then last user mode register, you change over to user mode in the reset handler, and then change this R13, because R13 of this user mode should also be initialized so that it points to different user mode stack. Okay, so otherwise you force the processor into system mode to set up the user mode stack, since both modes share the same register. Because from the reset you can come to system mode, okay, and then R13 of the user mode can be initialized, because R13 is shared among system mode and user mode, and then come to user mode. Okay, separate structure for each mode rather than using a single stack has a main advantage. What is the advantage? Errant tasks can be debugged and isolated from the rest of the system. So suppose there was a bug in the pre-fetch abort code. Okay, because of that the stack is corrupted, but data about our FAQ, okay, can function properly because their stacks are different and they are not corrupted. Okay, so you can isolate the problem to a particular mode. So that is the advantage of having different stacks for different modes. For safety reasons, it is always required to enable IRQ and FAQ only after their own stacks are initialized. Of course, it's a very valid. It's not only safety reason; it's a logical reason, right? Without using the initializing the R13 of each mode, if we enable the interrupt and if an interrupt happens, it will assume that R13 is already initialized, but it will be pointing to some random location. And if you try to save anything into that, you will get something out of it. Okay, you may have an abort because it may not be pointing to a valid memory. Please remember, in your system, a particular memory only will be valid. Not all the 32, no 2 power 32 addresses are valid in your system. So we need to first initialize the 30, R13 of all the mode. Then only you should enable the interrupts. So how do you assign interrupts? System designers can decide, okay, based on which hardware peripherals need to be connected to what. So accordingly, they should be initialized. They should be connected to a particular IRQ or FAQ. Okay. Standard assignments are various interrupts are given below. SWI are used for this is software interrupt is used for OS routine. IRQs are used for different purposes like serial port or timer, because IRQ is a physical interrupt input coming to the processor, and FAQ is another interrupt which is a fast response. So normally it is a single source is used because inside the handler we don't want to find out which interrupt source has come. Okay, interrupt can happen because of multiple sources. If you connect multiple sources to a controller and then the interrupt is generated. So FAQ is always connected to one particular source so that the handler will always assume, will know that it is from the particular handler and it can serve the interrupt without any delay. Okay, that is a normal convention. Handling of interrupts. Okay, it is a time in interrupt latency. You know that when the interrupt happens, from the time it is generated to the first instruction which is executed in the handler is what is time elapsed between this is called time interrupt latency. So based on the criticality of the source of the interrupt, latency needs to be minimized. So two goals are to be achieved by the system designer. Okay, which one of the interrupts should be connected where, and then how to minimize the interrupt latency. Okay. Okay, you need to handle the interrupts simultaneously. At the same time, you have to handle the latency also to be minimum. So nested handling means, suppose you allow one interrupt to IRQ handler, it comes into IRQ handler, and then inside that you enable IRQ, it will again interrupt the processor, and then one more handler will be called. The same handler will be called, and it will be serving the different source. Okay, so when you want to have a nested interrupt, the time taken will be more. Okay, and then another way is you can write a priority among different sources that you are connecting to IRQ, and then you can set them differently. So don't worry about this particular. I'm just giving you a heads up here. Okay, this will be discussed in detail in the next class. Okay, so don't bother about this if you don't understand what I mean by nested interrupt or priorities. If you already know, well and good. Otherwise, let us talk about it later. Okay, so we are coming to the end of the class here today. So we learnt about push and pop of thumb state. We learnt about conditional branches and then summary of instruction. Please go through this all these instructions in the thumb state, and this is the assignment. Okay, assignment, and then we talked about different exceptions and modes, and then how to set up different stack. Okay, this is a particularly very important. If you have understood this, then understanding the next class will be easier. If you don't understand this, it will be tough. Please spend some time because this is a very important part of the course. If you follow this, then only you will become a successful embedded engineer, because you should be able to write your own handlers. Okay, it is not enough if you write user code, then you will remain as a application developer. But if you want to become a system developer, system engineer, you need to know how to write handlers, how different bank registers are used, how reset handlers are written. These are all very important part. So to become from application engineer to a system engineer, we need to have an understanding of a good and a clear understanding of how different modes work and how different handlers are handled, how interrupts are handled. So understand this part of the course today. tomorrow or in the next section we will cover the interrupt handlers. Okay. Hope you had a good time here. I enjoyed sharing this information with you, and see you in the next class. All the very best with your lab sessions. Bye bye.